Hi everyone, Mr. Ahmed here. This video is the interpreting graphs lesson. There's a set of 7 examples starting at example 10 and going all the way to example 16 that I'm going to be going over. But what I recommend that you do is you just watch this first example right here. So example 10. Just watch as I go through it, kind of understand what I'm saying, then pause the video and then try the rest of those 6 questions on your own. Once you're done those questions, then maybe unpause the video and then maybe just kind of like, skip through a lot of my explaining and just try to find those answers as I write them on the screen here. Okay. Okay, so interpreting graphs, what does that mean? It really just means being able to read graphs, right? Just like looking at a graph and pulling information from it and being able to answer questions about it. Okay, that's really all it is. So let's just jump right in and you'll kind of see what I mean here. So for this first question right here, we've got the predicted population of a country, and we've got the number of years being on the x-axis, so the number of years from now, and we've got the population in millions on the y-axis. Okay, so right now we're at, I guess for number one, it's asking you what is the population now. So let's just do that one. So what's the population now? Okay, well, the population right now is exactly, happens at exactly 0 years from now, right? Because 10 years from now would be in the future, right? And 20 years from now would be in the future as well, okay? As would 30 and 40. Oopsie. As with 30 and 40, okay? But I don't want those. I want the population right now, which means 0 years from now. So all I have to do is I just have to find the part of my graph that has an x value of 0, okay? So when I look at my graph, I'm just going to say, okay, well, I've got my x is 0 right here, so I'm going to go up to my graph, and there you go. This is where my graph starts at time 0, at 0 years from now. I've got a population of 15 million. So that's what I'm going to write right here. So I'm going to say 15 million. Okay. Now find the estimated population in 20 years time. Okay, so that means 20 years from now, what's the population? You're going to do the same thing. You're just going to find the x value where this is 20, right? So this right here. And then you're just going to go all the way up until you hit the graph. There we go. Now, this to me looks like it's just slightly above the halfway point between 17.5 and 20. Now that halfway point is 18.75, so it looks like it's just above 18.75, so I'm going to say it's about 19 million. Okay, so that's about 19 million. Okay. Alrighty. Now let's talk about the gradient. So as I talked about it in class, right, the gradient means the same thing as the slope, which means the same thing as the rate of change. Okay? The gradient of a graph is going to be expressed as the vertical change divided by the horizontal change. Okay? So the vertical change of my graph between, two specific points divided by the horizontal change in my graph between two specific points. So let's take a look at what that means. So for example, I'm going to use this as my first point. Okay, I'm going to say this point right here, which we know its coordinates are 0, 15. I'm going to say that this is my first point. Okay, and then I'm going to go and look for a second point on here whose I guess coordinates can be very obvious, or where I don't really have to estimate the coordinates, right? And when I look through this, it looks like that second point is right about here, right? It looks like at about 25 years from now, the population is going to be 20 million. Okay? Okay. So now that I've picked those 2 points, I can just go and figure out what are the vertical change and the horizontal change to go from point 1 to point 2. Okay, so to go from point 1, which initially had a y value of 15, going from point 1, which originally had a y value of 15, to point 2, which now has a value of 20, that increase was an increase of 5. Okay, so I'm going to say that was an increase of 5 million people. Okay, now that increase of 5 million people happened in 25 years' time, right? Because we went from 0 years to 25 years, okay? So that means that my horizontal change going from 0 to 25 is 25 years, okay? And so this is a fraction that I can definitely simplify, right? I can divide top and bottom by 5, right? I get 1 over 5, which as a decimal is 0.2, okay? So this is 0.2 what? I can't just leave it like that. I do need some kind of units here, okay? So 0.2, and as we can see here, was actually million people divided by years. So this is 0.2 million people. I'm just going to write PPL for people per year. Okay. Okay, so that literally just means that every year there are 0.2 million people. The population is there's a better way of saying that. Every year the population is increasing by 0.2 million people. Okay, so that's what that means. All right, now find a formula for P as a function of T, time, in years. Okay, now as we saw in class, okay, all linear graphs can be represented through this equation right here. Okay, this equation right here, remember that m, as we saw in class, is in fact the slope or the gradient, and in here b is your y-intercept. Okay, and then x is going to be my independent variable and y is going to be my dependent variable. Okay, now here I'm not dealing with y and x, I'm dealing with p and t, right? Find a formula for p as a function of t. So p is going to be my y, so p equals, now my slope I already calculated it, it's 0.2, so I'm going to write 0.2, and then instead of x I'm going to use t, right? Because that's my independent variable. Okay, it's on that horizontal axis. So 0.2t, and then plus, and then I look for my y-intercept. Well, the y-intercept, we already figured it out, right? It was the population now, right? Your y-intercept happens right here. So that's going to be that plus 15. Okay, so there you go. That's your equation. Okay, so at this point, I do recommend that you just pause the video and then just do the rest of these questions. There's 6 more questions that you can kind of do on your own. When you're done those 6 questions, maybe just really quickly skip through my video until you kind of hit these screens where I've got all these answers up on the screen here, and then just double check to make sure that you've got the right answers. Okay? Alrighty, so I'm going to move on to the next question here. So in this question here, we've got a decreasing population over time. So let's do all the same steps. So what's the current population? Well, the current population looks like it's at about, what is that, 15, 16, 17, 18, 19, 20. Okay, so it looks like it's at about 18 million. Okay, so I'm going to write 18 million. Okay. And then estimate the population in 40 years' time. So 40 years from now, what's the population? So I get to 40 and then just make my way up to my graph, or my line graph, and then I just find the corresponding y value, right? So it looks to me like at 40 years we have about 6 million people. Okay, and so now they're asking us to determine the gradient of the graph. So what I'm going to do here is I'm going to choose 2 points on my graph that, you know, the coordinates look kind of straightforward, right? I'm going to choose this first point right here because, you know, that one's really easy. That one was 0, 18. Okay, and then I'm going to choose, you know what? I'm going to go ahead and choose this one. Yeah. Yeah, I think that's okay. I'm going to go ahead and choose this one right here, just because it does look like it's clearly going through 10 and 15 as the y value. Okay, we typically don't recommend that you choose such a close point to the first point. Usually you kind of want to use a point kind of further away on your line graph. And I guess we could have chosen this point right here, right? Like 20. I mean, we could have, 20 looks like it dropped down to 12 million people. There were a couple other points that we definitely could have chosen. I just chose this one because it was very clearly going through 10, 15. So I wasn't like feeling like I was approximating, right? So let's just do that. So here we're going to go with the gradient. Now we know that the gradient is the same thing as the slope. It's going to be a measure of the rate of change, which is the vertical change divided by the horizontal change, okay, between those 2 points. So my vertical change is to go from 18 to 15. Now that's a vertical change of 3, but because we decreased, right, because you always read your graphs from left to right, okay, because we decreased, that change is not just positive 3, it's actually negative 3, okay? So negative 3 million people, okay, over, and then the horizontal change. The horizontal change was to go from 0 to 10, okay? So we went from 0 to 10, right? To go from this point right here to this point right here, we went from 0 to 10. And so that is just 10 years. Okay? And so your slope is negative 3 over 10, which is negative 0.3 million people and that's going to be per year. Okay? So this really just means that the population here is decreasing. Every year it's decreasing by 0.3 million people. Okay? And finally, provide a formula for P as a function of T. Okay, so P equals, okay, so again, we're going to follow that same idea, y equals mx plus b, right? Where again, m represents the slope, b represents the y-intercept, okay? Now the slope, I just figured it out. It's right here, so I'm going to write negative 0.3. And then instead of x, I'm going to write t, right, as a function of t. And then plus my y-intercept. Now, my y-intercept was the current population, where, again, the line starts, which was 18. Okay? And there you go. That's your equation. Okay? Now, what's really cool about these equations is you can actually use them to kind of solve out for any other value that you want on this line, right? Because once you get this equation, let's say that, for example, I was interested in knowing, how many people are there going to be, let's see, what is that, 22, 24, 26? Okay. According to my graph, it looks like 26 years from now, I'm going to have about 10 million people. Let's double check and see if that's accurate. Okay. So what I'm going to do is I'm going to say negative 0.3 times, and we said we were going for about 26. I don't know if that's really that accurate. It looks like it's at about 10 million, but hey, we're going to find out in a second, okay? So I'm going to say negative 0.3 times 26 plus 18. There you go. That's kind of what I could tell, right? We weren't going to be at exactly 10, but it looks like we're at about 10.2, okay? But see, that's why this is really powerful, right? Because now that you've got this function, you can just solve for any one of these values on your line graph, right? You can solve for 30 years from now, 40 years from now, 32 years from now, 49 years from now, and so on, okay? Alrighty, let's move on to the next question. Okay. Number 12, so now we're looking at distance traveled versus hours of driving. So how far does one travel after 3 hours of driving? Well, at 3 hours of driving, it looks like we've traveled 150 miles. There you go, that's the answer, right? After 1 hour of driving, it's 50. After 2 hours of driving, it's 100. After 3 hours of driving, it's 150. So 150 miles. Okay. What is the relationship between hours of driving and distance traveled? So really, they're just asking for the slope. Now, hours of driving and distance traveled, again, you're going to go for that vertical change, right, divided by the horizontal change. Okay. Now, in this graph, it's actually kind of clear. It's a lot easier than the first two graphs because of the fact that our graph goes right through the origin, right? We start at 0. And after 1 hour, we've increased by 50 vertically. After 2 hours, we've increased to 100. After 3 hours, we've increased to 150. So each increment of 1 hour that we drive, we cover a distance of 50, right? So I cover 50 hours, I cover 50 miles at after 1 hour. After 2 hours, I go up by another 50, right? So from 1 to 2, that's 1 hour that's elapsed, right? So I'm going up by 50 for an hour. I'm going up by 50 for an hour. I'm going up by 50 for an hour, okay? So my vertical change is going to be 50 miles over 1 hour. So really, I can just say 50 miles per hour, okay? So there's your slope. If someone drove for 7 hours, how many miles would they have covered? Well, you have it on the graph, right? But you also know that you're traveling 50 miles each 1 hour, so 50 miles times 7, right, is 350. But you do have it on your graph, right? So you're just going to go and find hours of driving 7, and then you're going to go up to your graph, and you're going to go across to the corresponding y value, right? That corresponding y value is 350, so 350 miles. Okay? And then represent the distance d traveled as a function of the hours h spent driving. Okay, so I'm going to say d equals, okay, now again you're using y equals mx plus b, right? So maybe I'll write it one last time. Y equals mx plus b, where again m is the slope and b is the y-intercept. Now here, the slope we already found was 50 miles. So I'm going to say 50, and instead of x, I'm going to write down h, right? Because h is our independent variable. Plus the y-intercept. Now, this line, right, this graph actually goes right through the origin, right? So technically, I could write plus 0, right, because it goes through a y-intercept of 0. But that would be kind of redundant, right? Why would you write plus 0? That's kind of nonsensical. You might as well just leave it as d equals 50h. And there you go. That's your function. Okay? Alrighty, let's move on to the next question. All right, so this question here is about technology adoption rate, years from now, users in millions. Again, same type of question. How many users are there currently? It looks like about 10 million. So 10 million. Okay. Predict the number of users in 15 years. So you're just looking at 15 years from now. You go up to your graph, and then you're going to go across. And that looks like it crosses exactly and neatly at 60 million. Okay. Calculate the slope of the graph. Okay, so the slope of the graph is going to be the vertical change divided by the horizontal change of 2 points that we find on the graph. Now here, I know that I start at 0, 10, so that could be 0.1. It doesn't have to be. Just to be clear, it doesn't have to be. It could be another point on the line, but why? This one's very clearly a nice starting point. We see the coordinates very clearly, so we may as well use it, right? That's the criteria. Whenever you pick 2 points on your graph, just make sure that you're picking 2 points that you can clearly see, okay, and whose coordinates are very clear, okay? Don't pick 2 points where you have to estimate or guess, okay? The second point that I'm going to go with is actually the point that we just covered right now with how many people there are or how many users there are in 15 years, right? In 15 years, it looks like our line was going exactly through 60. So I'm going to say 15 and 60 are the coordinates here. Okay, and I do the same steps for the slope of the graph, right? So I'm going for the vertical change to go from 0.1 to 0.2. Well, here at 0.1, my y value is 10. And at 0.2, my y value is 60. That means I went up a change of 50. So that's going to be 50 million. Okay. Now, the x change, or the horizontal change, to go from point 1 to point 2 equals the change to go from 0 to 15. That's an increase of 15. So 15 years. Okay. And now you can simplify this fraction here. So 50 over 15, I can divide top and bottom by 5. I get 10 over 3. And I could express this as a decimal. It would be repeating, right? 3.3 repeating. Or I can just leave it as a fraction. I'm probably just going to leave it as a fraction. Why not? So 10 over 3 million people. Oh, is that users? Okay, so million users, same thing, doesn't really matter, per year. Okay. Now here we're asked to express u as a function of t. So again, u equals the slope, which is 10 over 3. Okay. And then the independent variable, which is t, plus the y-intercept, which was 10. Okay, and there you go. Alrighty. Moving on to the next question. Example number 14. So we've got cost of pizza versus number of toppings. Okay, so we've got a pizza that starts at an initial cost of, looks like $10 when there are 0 toppings, and then it just goes up as you add toppings. Okay, great. What's the base cost of a pizza without toppings? Well, that's exactly what I just said. It's 10, right? At 0 toppings, we're at 10, it looks like US dollars. I'm just going to put a little dollar sign, okay? How much does a pizza with 5 toppings cost? So at 5 toppings, we're up to 20, so about $20. Oh, that's a 2. Maybe I'll erase that one and kind of write it a little bit better. That's a 2, so $20. What is the additional cost per topping, right? So how much does one topping cost, right? Well, when we're asking for that, how much does one topping cost? Like, what's the cost per one topping? That's really just the gradient, right? That's the slope. It's the rate of change, okay? Now, I do have 2 nice points, right? I had 0 and 10, and then I had 5 and 20, okay? So I'm going to go with the vertical change divided by the horizontal change, right? The vertical change to go from 10 to 20 is an increase of $10. And the horizontal change to go from 0 to 5 is an increase of 5 toppings. Okay? And so $10 divided by 5 toppings is going to be $2. Whoopsie. That one's a really ugly dollar sign. Let's maybe get rid of that. $2. There we go. Per topping. Okay. Write an equation for the cost of the pizza as a function of the number of toppings. Okay, so the cost, which is our dependent variable, equals the slope times the independent variable. Now our slope is 2. We already calculated that. So 2 times the toppings, which is capital T, according to this, plus the y-intercept, which is 10. Okay? So there you go. And again, this is powerful because now you can figure out the cost of any pizza for whichever number of toppings that you want. So for example, if I wanted 10 toppings, then 10 times 2 is 20. 20 plus 10 would be 30. So a pizza with 10 toppings would cost $30. Okay? So there you go. That's that question here. And moving on to the next question. Example 15. So here it looks like we've got something about water consumption. We've got liters and years. And it looks like as the number of years is increasing, the consumption in liters is apparently also increasing. Okay, that's fine. Calculate the current water consumption. So that means right now, well, that looks like it's at, maybe I'll just zoom in real quick, but it does look like it's at about the halfway mark. Yes, it looks like it's exactly halfway. So at 15, and then in 10 years, just because I'm looking at number 2 already, 10 years looks like it's at about 35. Okay, great. These are easy ones, so just line this back up and fill it out for you here. Okay, the current water consumption we just said was 15 liters. The water consumption in 10 years is, we said, 35 liters. And what is the rate of increase in water consumption per year? Well, this guy right here was 0 and 15, and this guy right here was 10 and 35. Okay, so I've got my 2 points. Okay, I can see that I increased from 15 to 35, right? That vertical change is what I'm looking for, right? So vertical change divided by horizontal change. The vertical change is 20, okay, to go from 15 to 35. And then the horizontal change is 10 to go from 0 to 10. And so the rate of increase is 2 liters per year. Okay, express water consumption C as a function of time. So I'm going to say C equals the slope times the independent variable. That is 2 times t plus the y-intercept, which is 15. And there you go. Okay. And finally, yes, this is the last question. So here we go. Perfect. Oopsie. Here we go. Okay. So here we're looking at a deforestation rate, forest area in thousands of kilometers squared, and then years. Okay, great. So what's the initial forest area? The initial forest area, we're starting at 10. So here you're going to say 10,000 kilometers squared. Don't just say 10 kilometers squared. Maybe I'll just write that down. I'll just write down 10,000 kilometers squared. I hesitate to write 10,000 like in numerically, like 1 0 and then followed by 3 zeros, just because, I mean, it is on the graph here 10, and I don't want you guys to be getting confused about that, right? So the y-intercept is 10, keeping in mind that this 10 is in 1,000 kilometers squared. Okay. Okay, so predict the forest area in 35 years. In 35 years, it looks like the forest area is going to be at 3. Yeah, so 35 is at about 3. So 3 and then 1,000, oopsie, kilometers squared. Okay, maybe I'll fix this one here. Here we go. These are not 11s. Ooh, I can see that could be an issue if someone decides to just pause the video right here. So maybe I'll just write that out then. 1,000 kilometers squared. Okay, determine the yearly rate of deforestation. So again, you're just kind of pick out 2 points. Happily, we've got a nice initial point right here, 0, 10, and we've got this nice other point that we were asked about, which is 30. Oh no, we were asked about this point right here, 35. Doesn't matter. It looks like it goes nicely through 30 and 4. Okay, so the vertical change here is going from 10 down to 4. Okay, so the vertical change over the horizontal change. We're going from 10 down to 4. That's a decrease of 6, right? We're going down 6. Now that's negative 6,000 kilometers squared. And then horizontally, we're going from 0 to 30. So that's an increase of 30. Okay. When I divide top and bottom by 6, I get negative 1 over 5. So this is negative 0.2 thousand kilometers squared per year. Okay. And then express the forest A as a function of time. So I'm just going to write A equals, and then I've got my slope, which is what we just calculated, negative 0.2. And then as a function of time. T is going to be my independent variable, so that replaces x, plus our y-intercept, which is 10. Okay? And that is those questions. So hopefully this made sense. All right, and that's it for today. Thanks, guys. Take care. Bye-bye.